Welcome back to the latest lecture session. A quick recap of, holistically, I guess. Let's take a step back and understand the bigger picture. We want to remove suspended solids, even those solids that are relatively small and won't settle down within a reasonable amount of time. And now we coagulated them by adding a coagulant, and we destabilize them and we let them flocculate, right? And then we want them to settle down. We have big enough flocks and we want them to settle down. So in that context, we saw that it's flocculant settling or type 2 settling. That's what is prevalent in the settling zone that we have. So here, we will come back to this later, but just the relevant aspects. So here we have, let's say, the inlet zone, and then the settling zone, and then the outlet zone or outflow zone. So the assumptions in the models or the aspects that we are going to talk about is that if a particle can, settle down within this settling zone, it is assumed to be removed. If it even comes here, we assume that the particle will flow out of the relevant tank or the sedimentation tank. So that's one thing to keep in mind. Why? Because later when we look at it, we will look at the particle coming through here, and we will see, because this is the maximum time available. So the particle will have two vectors in this direction and in this direction. So by the time it reaches this point, right, or covers this horizontal distance, it should have covered this vertical distance. Again, we will look at this later, but we already looked at this briefly in, not briefly, in some detail in wastewater treatment, relevant aspects. Here we will look at it briefly. So type 2 settling, as mentioned, type 1 is relatively rare. In general, you have particles of different sizes, more importantly, and then they will have different settling velocities. They move at different velocities, and also you have water conditions that are typically rarely laminar. So you are going to have, relevant eddies out there or different gradients in velocity. So the particles will form flocks after colliding, and thus they will agglomerate. So that's why we say that we have, or we will see this or experience this flocculent settling. It's not flocculation settling, it's flocculent settling, let's say, right? So what does this mean? So here we see a pretty good picture here. So here we have effect of particle agglomeration. So we have two particles, right? A relatively bigger particle coming out here. So if I look at this bigger particle probably would have been removed within this settling zone, right? This is the settling zone, right? This is my settling zone, let's say. And this particle B, which entered at a lower depth, would have gone through or out of my particular settling zone, and it would have been carried out, meaning it would not have been removed. Particle A would have been removed, particle B would not have been removed. But what happens? Different settling velocities and also even different fluid velocities there, and thus you have A and B agglomerating, colliding and agglomerating, now a bigger particle. So both settle down, and that too at a much faster or earlier time, I guess, within an earlier time. So this is the effect of particle agglomeration on settling, and this is what we typically see, especially when water is coming in to sedimentation tanks and such, right? That's one thing to keep in mind. Let's move on. So in the context of wastewater, we did talk about different flocks, but here the kind of flocks are going to be formed. Here in water, we are typically talking about inorganic particles or such, but again you can have some organic content too, depending on the type of source of water. So here we looked at wastewater treatment, I think pin flocks, magnified, and ones with the flocks with the filamentous microbes and such. Again, different types of flocks, but again this is slightly out of context, but I wanted to have one picture about flocks, let's say. So benefits of type 2 settling, this is what we just looked at in that other picture. The combination sees to it that the particle settles down earlier, or those particles which would not have settled out would settle out, right? So how do I look at it, or how do I use this to be able to model my sedimentation basin or such? So there are different models. Here we are looking at one settling column model. So in general, it's difficult to really predict what's going to happen because flow conditions are going to be different. the actual kind of wastewater that you are going to experience in your, not wastewater, actual kind of water that you are going to experience in your particular process might be different than what is available to you. That will typically be the case with wastewater, but with water, with surface water as the source, typically you can get the water sample. So again, the issue is with respect to applying this model, there are aspects about correlating or using the results from one sample and applying it to another sample. Again, but let's look at the most widely used one. So as mentioned, no good theory, but the second best is the settling column theory, and we want to choose a column which has a diameter long enough to avoid wall effects. Yes, that's one thing to keep in mind, and we are assuming that settling time starts at time equal to 0. So this is obviously a batch system, right? We will look at the figure. I think we have it here. Okay, so this is what we have, right? Okay, so when I say time equal to 0, how do I interpolate that, or what information is that giving to me in a continuous flow system? In a continuous flow system, this time in a batch reactor will be similar to this theta, hydraulic retention time, right? So samples taken at different depths and times, that's what we see here, different depths, and also at different this same depth at time 0, time 5 minutes, 10 minutes and such. We will look at that. Usually 15 centimeter diameter, that's fine. Height is equal to the depth of the proposed tank or greater, it is that we typically try to do. Sampling ports every 50 centimeters or so, and we looked at these kinds of plots in detail in wastewater relevant aspects. I request you to go back there and look at it, but we will only briefly look at it. Okay, percentage removal is plotted versus depth, right? Percentage removal is plotted versus depth, but before that we have to interpolate and such, and I think we did spend quite some time in that particular context there, right? So apparatus for settling, I guess this is what we have, and this is the sludge, and in the next slides we will look at some pieces of information or some figures. In that context, when we are looking at concentration, we assume that this sludge that has settled down is no more part of the mass of the solids that's in the column. For example, if this is the one initially, I know the concentration, how? The mass of these solids, right? Mass by volume of this particular system. Let's say after some time in the column, now it's at this height, the water is here, but this is relatively more clear here, and here I have particles, and here most of it has settled down, let's say, right? So when I'm trying to calculate it meaning the concentration of the solids in this particular system, I'm assuming that whatever has settled down is removed from the system, and I will only consider the mass of the particles that's out here, let's say. That's something to keep in mind. So again, as I mentioned, the clock time in your particular settling column is going to be similar to your hydraulic retention time, and the depth is similar. The depth is the same as the depth in your sedimentation basin, and the depth per time, let's say, that will give me an idea about the surface overflow rate. So the depth per time will give me an idea about the surface overflow rate. Again, surface overflow rate and such, we discussed this earlier. Let me see, I think I plan to discuss this after a few slides, let's see. Again, in general, surface overflow rate will give me an idea about that critical velocity, if I may say so, beyond which, depending upon the type of tank, if it's upflow or horizontal, either no particles will be removed or only a fraction of the particles will be removed and such. We will come back to this. In general, the effluent concentration, we are now looking at our settling column analysis, let's see. Effluent concentration will be equal to, right, the mass in the column by the volume of the column. That's what we understand, let's say, right. So after some time, let's say, earlier it was different particles of different sizes. So let's say initially this is it. After some time, let's say, so maybe here I have the smaller particles, and here I have the bigger particles, a mixture, and here I have my sludge. So what is my effluent concentration going to be? So it's going to be equal to this mass in this column, right, not in this zone, mass in this column by the volume of the column. That's going to be my effluent concentration. How do I get that? I will have to get that by integrating C dV by dt or dV by V, this is not T if I am not wrong, or C dH by H, I guess, right. So, that is something to keep in mind. Yes, let us move on, because keep this in mind, we will use this later, right. So, as I just mentioned, it is integral C dV differential volume by V. Yes, you have different concentrations at different volumes, that is what we are looking at, let us see, right. So, mass in column will be the concentration into that particular volume, let us see, and by the total volume of the column will give you mass by volume. Because cross sectional area here relatively uniform throughout the column, it will turn out to be integral C dH by H. H is the total height here. So, in the last what we set, when I say set, I am talking about the set related to the sedimentation. We discussed how it came through, I think using the information given by Professor Markham Benjamin. We looked at discrete settling and then used that to understand how to interpret and maybe use the data for the type 2 column settling. Here from Dr. Batchelor, Bill Batchelor, my advisor, we will look at the numerical integration method. So, from taking the samples at different ports at different times, we will first have a table. From that table you will interpolate it, and let us say we will get this graph. So, 40% graph, right, or 40% removal graph different times, 50%, 60, 70 and 80, let us say, right. So, here let us say, based on this time and the relevant height, I will be able to calculate the relevant surface overflow rate, right. So, that is something that we already looked at. Yes, as in we already looked at depth by time will give me the surface overflow rate depending on which time and such. But as you can see, let us say at this time, it is not that it is only 50% removal, you have different fractions of removal at different stages, let us see, right. So, how do I take this into picture? So, let us see how the equation came about. Yes. So, as I mentioned, data analysis using numerical integration method from my advisor. So, we have this, the mass or effluent concentration is equal to integral of C dH by H. This is what we saw earlier. This is from integral of C dV, mass of the relevant particles in that relevant volume, into the relevant concentration by the total volume, right. That is equal to this particular aspect. I am looking at the numerator here, integral C dH is equal to sum of C into delta H, let us say. I have different heights, yes. So, sum of C into delta H. So, what is that equal to? C into H1 minus H2, H2 minus H3, so on, Cn minus 1 to this. And that I can rearrange. I am going to take out the term H common, height will be common. So, C1 H1 plus C1 minus or C2 minus C1 into H2 and such, it is just rearranging the terms such that the common variable is the height here, let us see, right. So, that is something I have. So, C out, right, C out will be equal to, so I know that the concentration is going to be given by this, and this is nothing but integral of C dH. So, if I divide this by H, that is the effluent concentration. So, I will have to divide this by H. So, that is what I have, C out is equal to this. So, it is going to be divided by H, that is what we have, and that is what we saw earlier, let us see, right. So, now I would know that my graph is going to be something like this. It will have the different removal percentages and different removals at different heights and such, let us see. So, how do I get this removal percentage in the picture? So, here I am going to say that fraction removed is equal to C naught, this is not out, C naught or C initially present minus C I by C naught, right, or initially present. So, from this I can rearrange and get C I in terms of the fraction removed and the initial concentration. So, this I will go back here and plug it into this particular equation, let us see, right. So, for each case I can plug this in, C I is equal to 1 minus R I into C initial, let us say, this is C initial, keep that in mind. So, C out 2, I can put that in here, let us plug that in. So, 1 minus R out into C naught, this is not out, this is initial, is equal to the same case I am going to plug it in, and then we can cancel out C naught, yes, and then rearranging for R out, right, R out I see that R out is equal to this particular set of terms. Again, C naught cancel out and we are just rearranging. That's why it's 1 minus of this set of terms, right? Bring this R out to the right hand side and this term to the left hand side. So that's what I guess you see out here, let's see, right? And Hn is 0, H1 is H, right? And so thus we get this equation, let's see, Hn is 0 and H1 is H. So this equation simplifies to be this, and so this is what you will use. Let's say the R out will be this R1. Let me see where the equation is: R2 minus R1 by into H2 by H, R3 minus R2 into H3 by H, and so on. So let's see this. So for example, here we will have this curve. After getting this data, we will have this curve. By interpolation, you can see that this curve will represent the 40% removal. This curve will represent the 50% removal. Let's say if I am looking at this R1 is this 50% removal across the whole H, right? And okay, so here we see this 55% removal across this, and this midpoint will be your what, H2 or not H2, this H, I guess. This H will be the midpoint, right? And H3 will be the midpoint out here, and so on and so forth, let's see, right? And R2 minus R1, we have the percentage removals out here, and we will use that to get it out of there. Yes, so that's how it comes in. You know, you have 50% removal and different levels of removal. Let's see. Let's move on. So different types of settling basins, right? This is what we have. We already looked at this, typically rectangular settling tank, but as we know, people would not typically prefer rectangular settling tanks because of maintenance relevant issues. Think of this, you need long and narrow tanks, right? So all this area beside it relatively difficult to use or utilize, right? So that's the relevant aspect. So because of the type of scraper, yes, here you have the side view which will give you a better view. Let's understand this. Water is coming in, you have influent channels, let's say, and then the paddles, and then you have this sedimentation zone, and this rake arm which is going to rotate like this, right? It's going to rotate like this. Yes, and from the side view you see this, and here you see the sludge hopper or sludge collection, let's say, and here again you are going to see baffles all around because you want to promote laminar flow conditions. Again, we talked about this dead zones here and so on and so forth, let's say. Because ease of maintenance, obviously people will go for circular flocculation and sedimentation basins. And recently people have also been looking at dissolved air flotation. Well, this seems a bit counterintuitive. I want to see to it that there are quiescent conditions, stable conditions, no mixing, such that heavier particles come out. But what is this about dissolved air? Why will I pump in air? Doesn't that create an additional element here and maybe some turbulence initially? So obviously here we want to look at the cases when we have particles of relatively less density, let's say, and rather than settling them down, we are going to pump in air initially, such that, you know, these particles, let's say, which are of relatively less density, algae, some organic matter and such, will rise up. You know, here you can call that scum. So that's what you have here, flocculant or flocculation. And then here from the statuator you see that you have the recycle or injection nozzles for the air, and we will see this in here, this particular zone. We are going to look at it here. So here you have the contact zone, and here you have the effluent zone. So this is my air particle, dissolved air. As it goes up, you know, relatively less dense particles again will be taken up along with it, and it's going to move up here. So it's not really settling here, and then the float will be scraped, right? Obviously this case, if there is any wind, you are going to have issues with scraping, right? So that's why typically it's going to work in the covered kind of setup. Earlier we used to remove it at this water at this particular level, supernatant, but here we will remove it as subnatant. Again, here this area will be less, but again it depends upon the kind of system and which you are using, let's say. So primary design variables, always primary design, right? So if it's discrete, I am just concerned with what is the surface overflow rate or the critical settling velocity. Before we go further, I guess I should certainly talk about this overflow rate. So I think we looked at this upflow and so on and so forth, right? So if my particle is coming in through here along with my relevant water, so because of this increasing cross sectional area as I go up, and Q is equal to area into velocity. Q is the same and area is increasing, then velocity will decrease. So if this dimension, let's say if I am using the length here, so here it will be relatively lesser, but we know that gravity will be pulling the particle down, right? So here let's say it is like this, and as you see the velocity of flow of the fluid is decreasing as we go up, right? So here we see this is the settling velocity of the particle, which we calculated from the Stokes law earlier, and this is the velocity of flow of the fluid, let's see. So here let's say we see that the settling velocity is higher than the fluid flow, that's velocity that's going out or taking the water out, let's say, then obviously the particle will settle down. So if Vs is greater than Vf, obviously the relevant particles will be removed, 100% removal. If Vs is less than Vf, obviously 0% will be removed. But what is this Vf? I am concerned with not the Vf here, but at this particular location. So that's the V naught or the surface overflow rate, let's see, right? So surface overflow rate. From here you can obviously calculate the surface overflow rate. This is fine with our upflow. But what about our horizontal flow? So in this case, if this is the settling zone, this is the inlet zone, this is the outlet zone, we are only concerned with this particular case, and my particle is coming through here. My assumption is that if the particle settles by the time it reaches here, I am fine. So the particle will be under two vectors, one the horizontal one and the downward or vertical one, right? So this is due to the settling, this is due to the velocity of that fluid, let's say. So let's see how to go about that, or what is the critical one that's required. So it has to be such that, what is the height? This is the height. It has to cover this, right, in this particular time, right, a particular time. But what is the time, or this theta? I should have mentioned theta there. Theta I know is equal to V by Q, right? So here let's say I will use theta. Why is it? This particle is spending a total of theta minutes in this particular system. Within that particular time, it has to cover a distance of h in the vertical direction. Only then will it be removed or just be removed, right? So h is equal to h by theta is V by Q. V is equal to length into breadth into height by Q. So the Q will go up, let's see, right? So this is going to be equal to, after I cancel it out, Q by length into breadth, right? Q by the surface area, right? So again this is similar to this surface overflow rate. So if the Vs is greater than surface overflow rate, then it will be removed. If Vs is less, again depends here, unlike 100% and 0%, there is going to be a different aspect, as in it depends upon which height it is coming at, right? So a fraction will be removed. It's no such thing as 100% removal or such. Why are we assuming fraction or this? We are assuming that whatever particle is coming in, it's not concentrated, but it is uniformly distributed throughout the height. So that is why it's going to be fraction removal, I guess, right? Vs by V naught into 100%. So that's the percentage removal that's going to take place. Unlike this upflow where we get 100 or 0%, it's Vs by V naught into 100%, let's see, right? That's the relevant percentage removal for a particular particle, let's see. So in general, what are the different cases? So for type 1, we are only concerned with V naught. For type 2 settling, we are concerned with V naught and also how much time it's also spending, let's say theta or h. So it has to be combination of at least two of these three variables, let's say, right? So what is the critical settling velocity or such that we typically look at? It's 20 to 50 meters per day. So one is V naught, and let's look at it for different pollutant removal. If we are looking at only turbidity, this is the relevant value. And if we are looking at color and taste removal and high algal content, right? So we see that we are decreasing the V naught, let's see, right? So that's something to keep in mind depending on the relevant density and such, right? So let's move on. Again, algal content, you can look at removal by dissolved air flotation. Again, as you can see, the density is decreasing in this way, and thus it is also affecting the V naught here. Let us move on. So, primary design variable, as we mentioned, it is also dependent upon the time. So, typical time in sedimentation basin will be 4 to 6 hours, and depth, right, okay, depth or theta, or we are going to talk about h, I guess, right. So, that is what we have out here. Why is it? Because it has to be able to travel this particular depth in that particular time, typically 3 to 4 meters, let us say. Let us move on. So, other design considerations, typically circular is better because it is easier and skim floatable. Main aspect is less maintenance, right, and less construction cost. That is why it is universally much more used compared to the rectangular one, even though here in the rectangular one, according to the sedimentation theory, we make better use of the area, let us see. So, that is the thing that we look at. From the figure, we saw that it is relatively more difficult to remove the sludge. And inlet outlet, as we saw from some of the figures, I want to have uniform distribution. I do not want short circuiting. If I have short circuiting, that particular flow path will have particles that are spending lesser time. Obviously, if they spend lesser time, these particles will not be removed as efficiently as the particles in the other flow paths, let us say. So, that is something to keep in mind. How will I do that? I will have baffles or multiple inlets, let us say, right. Outlet hydraulic aided by having weirs along the length of the rectangular basins. Even along the circular removal basins, you might have seen weirs all along, let us say, right. So, that is something to keep in mind. What other design parameters? This is from CPHEEO manual. They give more generic information, but let us see, we looked at the basics, but because we are in India and need to be aware of what is happening here, we will also look at this aspect. Detention period, again 3 to 4 hours, yes. For plain sedimentation, more time. For coagulated sedimentation, this. But again, we are not going to use only these thumb rules. We actually have to calculate, and then you can look at the relevant thumb rules. Velocity of flow not greater than this. Here the units are different. I think there we saw 20 meters per day or some such value from the American Water Works Association relevant data. Tank dimensions, again we will design, we will not take the thumb rules. So, breadth fine, circular diameter not greater than 60 meters, generally 20 to 40. These are good, what do we say, practical aspects to keep in mind, let us see. Depth, again as we mentioned, 3 to 4 there, and here 2.5 to 5 meters. You do not want to have a very low depth, even though the design says that your sedimentation will occur within a relatively less depth. You do not want to have very low depth, especially in rectangular tanks. Why is that? So, let us say the flow comes in relatively higher, let us say, then what is going to happen? You can have scouring, that is not what you want. Also, if you have greater depth, what can happen is that the particles will experience more flocculent settling. So, that is one aspect to keep in mind, flocculent settling. So, that is what you want to do. So, surface overflow rate, again based on the above aspects you can get that. So, 12,000 to 18,000 liters per day per meter square, and for flocculated one obviously 24,000, you can have higher values, 24,000 to 30,000 liters per day per meter square, let us say, right. Flocculated, so they settle or efficiency is relatively better. And obviously slope rectangular is towards percentage towards the inlet, and circular I guess 8% slope here. We are talking about this slope here. So, with that I will end this session. Why? Because in the next one I will move on to the relevant aspect. Until now, what did we look at? We looked at removing most of the suspended matter and we settle them down. Even after that, we are still going to have some suspended matter that we still want to remove. Let us say even some of the bacteria and such, right. So, how do we do that? For that, we are going to use a filter, right, different filters. Earlier, we used to use cloth and have the water pass through it and such. So, again the principle is same, pores of lesser size and the water will pass through, and depending upon the size and the type of removal, different types of particles will be removed. It is not only the pore size, the mechanisms are going to be different. So, in the next session, we will look at filtration. So, with that, thanking you for your patience, I will end today's session.